So in this video, we're going to work on 5.1 and we'll see how far we get. So we've talked about how to find the antiderivative and we've talked about how to integrate. Those are tools that we're going to need in this section eventually, but first of all, we have to define what's called a definite integral. So the definite integral is the key tool in calculus for defining and calculating areas and volumes. In the world, we know how to do area and volume of certain objects, but calculus allows us to do other shapes that are more unusual. We also use it to compute quantities such as lengths of curved paths, probabilities, averages, energy consumption, the mass of an object, and the force against a dam's floodgates, to name only a few. So this is something you would use in physics a lot, and you might have seen it already because you guys, I know, are working on Physics 1, a lot of you. So first of all, we'll talk about area. Scenario, we want to find the area of the shaded region R in the graph. How can we find this area? So look at the blue curve here. So the blue curve has a shaded region underneath it. Now that region is bounded by the curve up above and then the axes on the other two sides. How do we find this area? Well, it's not a square, it's not a rectangle, it's not a circle, it's not something that we know how to find the area of. So what we could do, well, let's see. Well, so we would say here, none of our geometry formulas work. So the best we could do is we could approximate the area. So one option is to actually build a object that we know that surrounds this. So one option is going to be to build a rectangle that our area is contained inside of. Now the problem with this is pretty obvious. The area of this rectangle is quite a bit bigger than the area of the shaded region. So the answer is yes, but how do we make our approximation good or accurate? In this picture here, you can see that this box, yes, it contains our area, but it contains a lot of extra space that we don't want. All right, so let's go down here and see what we can do. Instead of just doing one rectangle, and by the way, we're going to do rectangles because they're the most basic and easiest to work with when it comes to calculus. You could do some other shapes, but they're not as simple for calculus purposes. So here you can see that instead of doing one rectangle, they've actually drawn out two rectangles to approximate that area. This is a lot better. Remember, our original rectangle was like so, went all the way out here, so it actually had all of this area extra as well. By doing two smaller rectangles, we're getting a lot better at our approximation, but again, we still have all this extra area that we don't really want. So if two rectangles improved our approximation, what we're doing now is we're trying more rectangles. So here we have 4 rectangles. They each have the same width, the same base, but the heights are all different. The heights are the function value at what we call the left endpoint. So for this interval here, they use the function value at 0 to get the height. For the second interval, they use the function value at 0.25 to get the height. And for the third interval, they use the function value at 0.05 to get the height. So they always use the left endpoint. So they didn't use 1. So this is what we call an upper sum, because it is obtained by taking the heights of the rectangle corresponding to the maximum value of f in each interval. So each rectangle is too big. That's another way of saying why this is considered the upper sum. It's an overestimator for the area. On the other hand, on this picture here, you can see that all of our rectangles are inside of our shaded region. That's because they're taking the right hand. So for this first interval here, they took the right hand value as the function value. And then for the second interval, they took the right hand value as your function value. So these became the heights of our rectangles. Notice here the function value at 1 is 0. So the height of that rectangle is 0. That's why there's no rectangle visible there. This is what we call a lower sum. So this is what we call an underestimator. So we overestimated with the upper sum. We can underestimate with the lower sum. All right, so that's those. All right. So So the upper and lower approximations are good as they give us a maximum and a minimum bound for what the true value is, true area is. Another possibility would be to consider the midpoint of each interval. So instead of choosing 0 as the height or 0.25 as the height, they went in the middle and they took the middle point, the middle function value, as the height for that rectangle. And they did that for each interval. They found the midpoint for each interval and then took that height as the height for that rectangle. Notice we are underestimating and overestimating, overestimating. So it's kind of in between the two. Notes. There are some characteristics in each of the above approximations which we should point out. The interval from a to b, so a is 0, b is 1, over which the function is defined was subdivided into n subintervals, each with equal width or length. So our formula for these subintervals, so in this case here, we had a was 0 and b was 1. So according to the formula, our subintervals, we call them delta x. It's the change in x. Eventually this will become dx for us, but for now we'll do delta x. The formula for this is you take your interval from a to b and you subtract b minus a and you divide by n. N is the number of subintervals you want. So in this picture here, and all three of these, you can see we had 1, 2, 3, 4 rectangles. So we had 4 subintervals. So if we do our b minus our a divided by the number of rectangles, this is the size of each subinterval. Excuse me. Fractions I know are nice, so let's write those. So you can see we go from 0 to 0.25. That's our first subinterval. And then from 0.25 we go to 0.5. Another 0.25 is a distance. Ooh, I got the chills. So each of these rectangles has the same base. Each rectangle has a base of delta x. So in order to find the area of each of these rectangles, what we would do is we would take the base, which is our delta x, and multiply by the height. The height depends on which version we did. We could have done the upper sum, the lower sum, or the midpoint sum. Which one you use determines your height for each rectangle, which method. So let's actually, let's see. All right, so here we go. Use finite approximations to estimate the area under the graph of this function using an upper sum with 4 rectangles of equal width. So we're going to work out one of those problems we were just looking at. All right, so let's see. This guy here, if I were to draw the picture, and I don't expect y'all to remember how to draw all these, but the basics you should be able to do. X squared means this is a parabola. Negative means it's a parabola opening down, and it's shifted up one place. So the parabola is up at 1, and it's pointing down. All right, so we're going to assume they want the area. Hold on, is this the graph we were just looking at? If it is, we can use their numbers. Wow, too far. All right, so yes, this graph is the parabola that we're looking at now. So what we're going to do is we're going to assume they just want the first quadrant because I didn't specify when I wrote this down. All right, so we're going to basically work out those first 2 problems that we saw with the 4 rectangles. So we're going to assume they only want this quadrant here. It should have specified, it should have said the graph under this curve in the first quadrant, but I forgot to put that apparently. So what we're going to do is we're going to create our 4 rectangles by creating 4 subintervals. Well, I just found out how big they are by doing this up here. Because this curve goes from 0 to 1 here. How do I know it goes to 1? Well, number 1, we have pictures that show us. But if you set this equal to 0, you can solve for your intercepts. So that's one of the first things we need to talk about. You're going to sometimes need to find the intercepts, or the zeros of your curve. So take your curve and set it equal to 0 to find where it intersects the x-axis. So if I bring my x squared around, take the square root, and we end up with plus or minus 1 equals x. So this is positive 1 here. This is this intercept. So what we're going to do is we're going to do the 4 boxes. So break this up into 4 intervals. 1, 2, 3. All right, so there's 4 subintervals. The picture, if you want the pretty picture, is, let's see, we're doing the upper we're doing this one right here. This is the upper sum. So these are my 4 subintervals on the bottom. They're each 0.25 away from the other. So that's my delta x. The height we get by taking the value on the left end, because that's where the function is going to be the biggest value in the interval. Take the left end point for each, and we're going to plug all of those into the function to get our function values. But they already did that. It's actually right here. So if we plug in 0 to our function in our problem, we get 1. We plug in 1/4 or 0.25, we get 15 over 16. If we plug in 0.5, we get 3/4, and so on. So, whoopsies. Come on. Control Z. Okay. So how do we get the total area? So the area under this curve is going to be the base times the height for each of our rectangles. So remember, we're doing 4 rectangles here. Each one is going to use the height of the left endpoint. There you go. Those are our 4 rectangles. So we take the base times the height for each rectangle. So the first rectangle, the base is delta x, and the height is f at the left endpoint, 0. The second rectangle is the delta x, and then f of our second endpoint. So that's 0.25 away. So from 0 to 0.25, so 0.25, plus delta x times f of the next endpoint. So another 0.25 away would be a total of 0.5 away. Oops, delta x. Plus delta x times f of, well, another 0.25 added would be 0.75. Oh. So I'm just using these values, 0, 0.25, 0.5, and 0.75 as what we plug into the function. This is what we traditionally call the left-hand sum. In your homework, you probably will not draw the picture out. You're probably going to calculate the left-hand sum and the right-hand sum, which I'm going to do down here. And then you're just going to look and see which one gives you the bigger answer, and that will be your upper sum. The smaller answer would be your lower sum. All right, so notice all of these have delta x. So what we can actually do is factor delta x out and just multiply the answer of all of these numbers added up by our delta x. This makes your problem a lot easier. So in general, when you're trying to find the area under the curve using rectangles, you simply find the height of each left-hand endpoint, and then you add them all up and multiply by delta x. So delta x, remember, was the 0.25 or 1/4, either way. The f of 0 is 1. If you plug 0 in here, you get 1. If you plug 0.25 in here, you're going to get 1 minus 16, so that'd be 15 over 16. If you plug 0.5 in here, that'd be 1 minus 1/4, so that would give you 3/4. And if you plug in 0.75 here, that'd be minus 9 over 16, so 7 over 16. I want to make sure I got that right. Yeah, okay. All right, so add these numbers up and multiply by 2.25. So 0.25 times, this calculator doesn't do fractions. Oh, I know how to do it, okay. Calculator. So 16 plus 15 plus 4, that'd be 12 plus 7. All right, 50 over 60, 50 over 16, but I can reduce that to 25 over 8. So the sum of all these is 25 over 8, if I'm not mistaken. And then we multiply by 1 over 4, or 0.25, so that'd be 25 over 32. This is the area under the curve approximated by the left-hand sum, which actually turns out to be our upper sum, but you're going to see why, because we're going to do the opposite as well. All right, so let me show you a way to organize this if you did not draw the picture. So let's suppose you don't know the picture, and let's do this. So we are going, well, you do need the interval. So the interval is from 0 to 1 again. So if your interval is from 0 to 1, what you're going to do is you're going to break this up into 4 sections. So here are our 4 sections. They're supposed to be equal width. I didn't draw it to scale. Your delta x, the width of each of these sections, is the formula b minus a over n. Well, our interval that we're going to look at is from 0 to 1, just like we did before, this quadrant here only. So that means 1 minus 0 over 4 rectangles is 1 over 4, or 0.25. So what you do is you just do your value. So from 0 to delta x is 0.25, and keep adding that. So you get 0.5 and 0.75. Now, we're trying to do the right-hand sum this time. It says do the lower sum, but you are generally not going to know which one is the lower sum until you try. Right-hand sum. Which means we're going to use, for this interval here, we're going to use the right-hand value to get the height of that rectangle. For the second interval, we're going to use 0.5, the right-hand value, and then so on. All of these are the right-hand, so we're going to leave out the left value. In the previous problem, we left out the 1. Notice we didn't use the right-hand value. In this case, we don't use the left-hand value because we're doing the right-hand sum. So the area, again, is always going to be delta x times your function evaluated at each of your endpoints. There you go. Well, we know what delta x is. We found that, 0.25 or 1/4, either way. F of 0.25 we get by plugging 0.25 into our function, and that was 15 over 16, plus plug in 0.5, and we got 3 over 4. Plug in 0.75, and we got 7 over 16. So I'm just plugging it into this f of x here. Plug in 1 minus 1, that gives us 0. Remember that one picture where there was no height of the rectangle? I'll actually show you real quick. So we're doing this one here. This is the problem we're doing now. See how this rectangle has no height? That's because the function of the right endpoint, the function value at the right endpoint is a value of 0. All right, if we add all these together and multiply by 1/4, let's see, that would be 22 and 12 make 34. Make sure you get a common denominator here, or punch it in your calculator and get a decimal, which we can reduce. Let's see, 34 divided by 2 is 17, divided by 2 is 8. So we end up with 17 over 4 times 8 is 32. So this is the area for the right-hand sum. Now that we have the left-hand sum and the right-hand sum, you can see that this must be the upper sum and this must be the lower sum. So the actual area is less than our upper sum, but greater than our lower sum. Somewhere between those two. It's not that big of an interval, honestly. All right, I think that's all I had on this whiteboard. Pink. Whoa, what happened? I don't know what just happened. Let me pause while I fix that. Alright, so now we're going to use finite approximations to estimate the area under the graph of the function using the midpoint of each rectangle's interval with 4 rectangles of equal width. Alright, so the midpoint, we also saw the picture for this on the other screen. It's on my other screen, so I actually can't go to it, but you guys have it on your notes, I hope. So midpoint, again, we're going from 0 to 1. We're going to break it up into the 4 subintervals. So remember, our delta x was 0.25, 0.5, and 0.75 using delta x. It's the same delta x as before. However, this time we need the midpoint. So the midpoint is the value that's halfway between each of these intervals. This is what we're going to use to find the height of each of these rectangles. So what is halfway between 0 and 1/4? How about 1/8? And then what I'm going to do is I'm just going to add delta x to get each of the other midpoints because they're all halfway in the interval, so they're the delta x away. So delta x is 1/4, or if I make it a common denominator, oops, it would be 1/8 plus, it'll be 2/8. All right, so we're gonna add 2/8 each time. So this is 3/8, 5/8, and 7/8. So to find the area, using this method as approximation, you're going to do delta x times f of 1/8 plus f of 3/8 plus f of 5/8 plus f of 7/8. All right, delta x, the same as before, it's the 0.25 or the 1/4. And these you find by plugging them into here. So 1 minus 1/64, so that would be 63/64, plus 1 minus 9/64, so 64 minus 9 would be 55/64, plus 1 minus 25/64, so 64 minus 25, that would be 39/64. I should probably be using my calculator, but I'm not. 64 minus 49, 15/64. All right, so those are our function values. So we're going to add up all of them, and we're going to multiply by 1/4. So let's see, that'd be 8, 17, 22. So 8, 13, 16, 17. So 172/64. Hopefully I did that right. All right. This can obviously reduce. So divide by 2. That would be 86. Oh, give me a calculator. Make sure I got those right first. 63 plus 55 plus 39 plus 15. Yes, 172. Divide by 2. Divide by 2 again. All right, so if I did reduce by 4, 4 goes into 172, and we end up with 43. So the area that we get is 43/64. Now the other areas we had a denominator of 32. So if I were you to compare this, I would expect this to be somewhere between our upper and lower sums. Turn them all into fractions to find out for sure. All right. Example, compare the results of using upper sum, lower sum, and midpoint rule to estimate the area under the curve. Okay, well, I guess I get to go get those. So the upper sum, the lower sum, and the midpoint. So if I turn the midpoint into a fraction, a decimal, 43 divided by 64 is 0.6719 if I round to 4 decimal places. Let me go get my other two. Where is it? Should be this one. All right, we got 25 and 17/32. and 17/32. All right, so let's turn those into decimals. So 25 divided by 32. That's 0.7813. And 17 divided by 32 is 0.5313. All right, so I was right. Now, it's not always going to be true that the midpoint is halfway between. This curve is a very specific shape. It is a curve that is descending. So the upper will always be the left endpoint, and the lower will always be the right endpoint of each rectangle. The midpoint is going to be literally halfway between those because it's halfway between your upper and your lower value in that interval. This only happens when your curve is monotonic, remember that word? So only decreasing or only increasing, that's when midpoint will be specifically exactly in the middle. If your curve is doing all sorts of crazy stuff, your midpoint could be here or your midpoint could be here. It could be either extreme or it could be somewhere in the middle. You never know. It depends on the curve. So that's why I say find the right-hand sum, find the left-hand sum, and then the bigger one is going to be your upper sum, and your smaller one can be the lower sum for our course. Other courses have different definitions of upper and lower, but that's how ours is going to work.